This is another example that we can analyze. Imagine that you have an infinite line of charge. So the charge, of course, produces an electrical field, and you know what is the electrical field applying Gauss. You know that you will construct a surface, a Gaussian surface with symmetric. It goes to the center. Okay, it's not well drawn. The line goes through here, okay, through here, okay, like this to the center, okay, this is the line. So I will apply Gauss law, and if I apply Gauss law, let me erase this one, let me erase this one. If I apply Gauss law, I will find that the flux is only happening on the lateral surface. There is no flux here because it will be E. I suppose that E will go, if it's an infinity line, I would suppose that the electrical field will go perpendicular to the line. It will be like this. Well, DDS will go like this. So E scalar DDS for the two tops will be 0. So the A by the area will be the charge inside divided by epsilon 0. So E by the area is, this is the R, this is L, so the area is 2 pi R by L, this is the area of the surface, equal Q inside, that is sigma by, not sigma, lambda, the charge per unit of length by L, this is the charge inside divided by epsilon 0. So I will have that E is equal lambda divided by 2 pi epsilon 0, 1 over R. This is the electrical field, and of course it's going in the R direction. This is the R direction that I have naming here, like this. At any point P, this is the R direction, okay? It's going all the way, the electrical field is going like this. So this is the expression, we have the magnitude here. But what if we want to find the potential at any point? I cannot use it. V of P equal the integral of d dq divided by RK, because this is I cannot, at the point P, to find at the point P, at this point P, the contribution of the potential R, I cannot find because I cannot fix the potential at the infinity equals 0. So better we don't use this equation. I will use this equation, ddv equal minus the integral of E scalar ddr. So ddv equal minus the integral of lambda 2 pi epsilon 0, 1 over R, the electrical field, R scalar ddr. But R scalar ddr in this thing is ddx, is this direction, okay? Because this is the R, the ddr, I'm going like this, so it's like using this system of reference, dx. So ddv, well, we can use the R, the distant R. ddv will be lambda divided by 2 pi epsilon 0. R scalar ddr will be ddr, integral of 1 over R ddr, the minus sign, so the integral will be ddv, the integral will be. So now maybe we do it like this. Maybe we do it better like this. We have this equation. ddv is minus E scalar ddr. And this equation has led us to the change in potential is minus E, that is lambda divided by 2 pi epsilon 0, 1 over r by ddr. So what I will do, maybe I will do like this. So this is ddv is er ddr. This is minus er ddr. So maybe I do it like this. Er is minus the derivative of v respect to r. Maybe it will be easier to do like this. Er will be minus the derivative of v respect to r. So for one side, I have that the electrical field, the radial component of the electrical field, radial in the sense going out of the cable in the perpendicular direction is minus lambda divided by 2 pi epsilon 0, 1 divided by r, and this must be, sorry, this is the electrical field ER, the component of the electrical field in the radial direction, and this should be equal minus the derivative of v respect to r. So I will think, what is the function v of r? That when I make the derivative, I will get this, and the function is lambda divided by 2 pi epsilon 0. So I need to make the derivative, and to find this, so I need to put log of r, because the log of r, when I make the derivative, I will have this. But I need to put the minus sign, because the derivative of v respect to r is equal minus lambda divided by 2 pi epsilon 0, 1 divided by r. So if I put the derivative, yes, it will be, you can derive this function, and you will obtain this, yes, plus v0. You can derive this function because this is a constant, so v of r will be like this. So as you see, if you want, I can write like this. V of r is v0 minus lambda divided by 2 pi epsilon 0 by the log of r. The log of r is a function that when r equals 1, the log is 0, and the function goes to infinity when r is go to infinity. So log of r goes to infinity when r goes to infinity. It's go to infinity very, very slow because the slope is very small of the log of r. Okay, but it will go to infinity. So can you choose a point? This is my question. Can you choose v of r to be 0 at r at infinity? Well, it's impossible. You can see for this equation that you cannot choose v of r to be 0 at infinity, because when you go to the infinity, the log of r is going to the infinity. So you will have some amounts of potential at some points, minus something that is infinity, the potential will go to infinity, but you want to go to 0, cannot go. So you need to choose a point. If you want to choose a point where the potential is 0, at some point you will do like this. Let's say that I want to choose r equal a, some points, where v of a is 0. So I will plug this equation and I will find my v0. So I will say v of a will be v0 minus lambda divided by 2 pi epsilon 0 by the log of a. So I want this v of a to be 0. So this 0 will be v0 minus lambda divided by 2 pi epsilon 0 by the log of a. So v0 will be lambda divided by 2 pi epsilon 0 by the log of a. So v of r will be v0 lambda divided by 2 pi epsilon 0, the log of a, minus, you go here, you go to your equation, you have a just a constant 0 minus lambda divided by 2 pi epsilon 0 log of r. And this is the function that you can construct for this case. So what I have done is like this. I have a star with a electrical field like this. I have said that E scalar ddr is minus ddv. I have said that E sub r by ddr, when you make the dot product, you will have E sub r by ddr. The component, the radial component, by ddr is minus ddv. So E sub r is minus the derivative of v respect to r. From here, you see that. So I have a star with the electrical field that I know from Gauss' law that this is the electrical field. I have obtained v of r. Perfect. I have realized that when r tends to infinity, the log of r tends to infinity. So I cannot adjust the point at the infinity should be 0. When r is in the infinity, how can I make v of r equal 0? Cannot make it. So it's not possible to choose this point, the point at the infinity as the 0. So, but what I have done is that we can adjust the point at some points a to be v of a equals 0. How? I take my equation v of r is v0 minus lambda divided by 2 pi epsilon 0 log of r. I evaluate by the point v of a and impose the condition that at certain point a, r equal a, at distance a from the cable, from the wire, v of a is 0. So this equation allows me to find what is v0. So now the vr will be the equation that I wrote. V of r is here. V of r is the v0 minus lambda 2 pi epsilon 0 log of r, log of r. Okay, and this is the equation. This is the potential that you can write for a long wire of charge with the condition V of A equals 0. So you should add this condition. Okay, that's all.